Hello, we're now in section 2.6 where we're going to talk about linear transformations, and we're going to continue this idea of the telephone booth that, just like Clark Kent went in and he came out as Superman, this boxy thing is a place of transformation, and we're going to send vectors through different transformations, and some of them have some really special properties. We've already seen that. And in this section, we really focus on a class of transformations called linear transformations. They'll be pretty prominent, and you'll see why towards the end of what we talk about today. So take a look at these three vectors, and looking at them, we can see immediately that they have a pretty special relationship, that the first two, if you add them together, equals the last one. A question that I want to pose is, we know that this plus this equals this. What if this goes through a transformation, and this goes through a transformation, and they're going to come out as certain new vectors? This then goes through the transformation, and that's going to come out as a new vector. The new vectors, as they come out, will that relationship still hold, where you can add the first two and get the third? So, and we can say it symbolically like this. This is the big question. Will the transformed vector 1, 1 plus the transformed vector 2, 2, so these will be some totally new vectors. If you add those together, will the sum of those equal the transformed vector 3, 3? And the answer is sometimes it will, sometimes it won't. Let's look at a couple examples and kind of compare them. So the first example we're going to look at is going to be defined by the transformation. You have a vector xy, and the transformation looks like this. The top element will be x minus y, and the bottom element will be 3x. And this is the whole way it works. So let's see where each of those vectors go. 1, 1 is going to be 1 minus 1 over 3 times 1. And that's 0, 3. And then 2, 2 is going to go to 2 minus 2 over 3 times 2. And that's 0, 6. And then the last one, 3, 3. is going to go to 3 minus 3, and then 3 times 3, which is 0, 9. And these are the transformed vectors. So the vector 1, 1 through the transformation ended up at 0, 3. The vector 2, 2 through the transformation ended up at 0, 6. And 3, 3 went to 0, 9. And we can see right off the bat that these two vectors went through the transformation, and their sum is still this third vector after it went through the transformation. So here, yes, things that added together to a third vector, even after going through this transformation, they still added together to that third transformed vector. Okay, this time the rule for this transformation in our second example is going to be you throw in a vector xy, and the transformation spits out the vector xy, y. So the vectors that we've already seen, t of 1, 1 will get sent to, looks like 1 times 1, 1. So that's nice. That's just 1, 1. And then the vector 2, 2 will get sent to 2 times 2, 2, which is 4, 2. And then that third vector, 3, 3, it will get sent to 3 times 3 over 3. And that's 9, 3. And so we do this check. Are the so the 1, 1 got sent here, the 2, 2 got sent here, and the 3, 3 got sent here. Is it the case that these two add up to the third one still? And 1 plus 4 is not 9. Okay, we've got a breakdown. So here in this transformation, no. it wasn't the case that when we transformed those vectors that they still added up to the third vector. So t of the transformed 2, 2 vector, added it to the transformed 1, 1 vector, and they did not equal the transformed 3, 3 vector. And so this is a little bit different. So to answer this general question, will transformed first vector plus the transformed second vector always equal their sum? And the answer is sometimes yes, sometimes no. If it is, so we'll say sometimes yes. And when that does happen, this is called a linear transformation. And when it doesn't happen that way, like in the second example, so sometimes no, it's still a transformation, but it's not linear. Okay, still with this transformation, since this one was working out so well so far, I want to look at one more thing. So obviously we know that 5 times vector 1, 1 is 5, 5. And so a question that we could ask is, can you take 5 times the transform vector, and will that equal the transformed 5, 5? So the question is, will 5 times the transformed vector 1, 1 equal the transformation of 5, 5? In other words, can you kind of slide these scalars in and out and still keep this type of inequality? Up here, we were able, with this transformation, to you know, add them before the transformation or add them after the transformation, and it would still sum to that vector 3, 3 or the transform vector 3, 3. And so this question is asking, can sliders move in and out of the transformation and still keep the equality? Well, we know this guy's out of the game. He couldn't even do the sum part. But let's check out this guy and see if, at least in this case, that holds true. So 5 times, let's see, the transform vector, we already found that was 0, 3. 5 times 0, 3 over here. And then the transformation of 5, 5 will be 5 minus 5 times 3 times 5. And that's 0, 15. This guy over here, 5 times the vector 0, 3 is 0, 15. Awesome. So those worked out. In this case, we could, that 5, it didn't matter if you multiplied it before the transformation or, so here is where you're multiplying it before the transformation, or if you multiply it after the transformation, you still are getting the same thing, the 0, 15. So let's write out the formal definition of these transformations that are linear. If you have a vector u and v and they're elements of the vector space Rn, and c is a scalar, then a transformation. And remember, transformations in the olden days, when we were back in, just Algebra 2, we called these functions essentially. But here in linear algebra, we call them transformations when we're moving from vectors to other vectors. And a transformation, and we can call it T from Rn. We don't always have to stay in the same vector space. It can move between vector spaces. Is said to be linear. A linear transformation if the following holds true. If you have t, if you take the transformation of the sum of two vectors, so this would represent that 3, 3 vector that we talked about earlier, then that's equal to the transformation of the first vector plus the transformation of the second vector. So things that were adding up together before the transformation need to still add up together after the transformation. And then the other condition for it to be called a linear transformation is the second one we saw, where you have the transformation of a scalar times the vector u, and that's equal to just a scalar times the transformed vector u. So that scalar, it doesn't matter if you multiplied it before or after the transformation, that it would still hold that inequality. And one reason we're interested in this property, these abilities, these two special abilities, is because these, no, not that, these will, if a transformation follows these rules, then it will preserve the structure of the vector space structure. So these transformations are taking these vectors, u and v, and here's the vector u plus v. And transformation takes them to, maybe it's the same vector space, but it could be a different dimension too. U is going to go to tu, v is going to go to tv, and so when we say that we are preserving vector space structure, all of this probably looks somewhat familiar, because when we used to talk about closure of vector spaces, we definitely were always talking about vector addition and scalar multiplication. Those types of discussions were just slightly different, but definitely related. So when we were first discussing the ideas of vector spaces, we knew that if u and v were in a set, then to be a vector space, u plus v had to also belong to w, and any scalar multiple of any of those vectors had to belong in w. It had to be closed under vector addition and scalar multiplication. This was the closure of vector spaces. And here we're saying that if a transformation is going to be linear, that it has to preserve these vector additions, the idea that if they added up to a certain vector before, after the transformation, they have to add up to the transform vector. And if this scalar multiple, you know, if something was a scalar multiple of a vector before the transformation, it has to be a scalar multiple of that transform vector. So it has to, after the transformation, it still has to hold that scalar, it has to be a scalar multiple. So the olden days, these properties here were just showing the closure of vector spaces. And this property here is a transformation that preserves vector space structure. So I didn't want you just thinking, oh, we've already talked about this. It's a slightly different idea that because this transformation is preserving the vector space structure, that we spent some time talking about what is the vector space structure. It's this right here, this closure property. So I want to bring up something important that we need to note at this point. And we haven't talked really about these since the last section, 2.5, but the matrix transformations that we saw back in 2.5, they are linear transformations. And in fact, anything that you can represent as a matrix transformation is a linear transformation. And you can say, well, wait, what about this? This is a matrix transformation. That's not what I mean. This is not a matrix transformation. A matrix transformation is... Okay, this was a matrix transformation where you have a matrix and you're going to multiply it by each of your vectors, and that's going to represent the transformation. We probably had some other ones. This is a matrix transformation. Anytime you're taking a matrix and multiplying it by a vector, that's a matrix transformation, and those are all linear transformations. So all matrix transformations. This is a transformation where you have a certain matrix being multiplied by your input vector. All of those guys are linear transformations. They all follow the rules that we just talked about of linear transformations. So this guy right here is not a matrix transformation, and it's not even a linear transformation. This actually isn't a matrix transformation, but we're going to see if we can write it as a matrix transformation, and we will be able to. And it also is a linear transformation. So not only is this true that all matrix transformations are linear, but even more powerfully and conversely, all linear transformations can be represented as matrix transformations. So all linear transformations can be represented as matrix transformations. So essentially, when you see a linear transformation, you can be assured that somewhere there's a matrix that represents that linear transformation. And conversely, when you see a matrix, it's representing some sort of linear transformation. So these two classes of things are actually identical. Okay, we've got a lot of theory going on here. This definition of what a linear transformation is, and the idea that essentially if you see a matrix, that really is a linear transformation. Let's get back to an example and make things a little more concrete for a minute. So earlier we saw that this transformation defined by the first element minus the second element, and then 3 times the first element. This is, in fact, a linear transformation. And we're asked to find the matrix that represents this transformation. Because it's a linear transformation, we know that somewhere out there there's a matrix that will represent what's going on with this transformation. And so this is what I mean, that there's some matrix that when I multiply it by 1, 1, that I'll get that 0, 3, that this transformation was sending 1, 1, 2. So I think through, okay, what numbers need to go in here? I know that this top row here combined with this column will equal a 0. So I can kind of see that a 1 and a negative 1 here would do the trick to create this 0. So that looks like that is a good candidate for the top row. 1 and negative 1. And then I need, this 3 was coming from the x always. And so how about 3 times x and no y involved there. Let's make sure it works out with the other vectors. And so when we take this matrix and multiply it by the vector 2, 2, we get the 0, 6 that we need, and then when we multiply it by 3, 3, we get the 0, 9, and that checks out. These are kind of funny vectors to test it with because the x and y's are the same, but if we were to try really any two-dimensional vector, this matrix would represent that transformation. So this was the matrix that we were looking for. I want to think for a minute, where does this transformation take the standard basis of R2? So 1, 0, 0, 1, those two vectors, this is the standard basis of R2. And just think about this formula for a minute. T1, 0 will be 1 minus 0 is 1, and 3 times will be this. And t of the other element in the standard basis will be 0 minus y is negative 1, and 3 times x is 0. Okay, so you probably recognize something. These are actually the columns of this matrix that represents the linear transformation. So this is true always, that wherever the transformation takes the standard basis, that those are the vectors that make up, or those are the columns that, those vectors are the columns that make up the matrix that represents the transformation. So this will give us a method for finding the matrix of any linear transformation. So the image of each of the standard basis members, vectors, so the image of this guy was 1, 3, the image of this guy was negative 1, 0. Each of those images, you know, after they go through the transformation, is a column in the matrix that represents the linear transformation. So the method for finding the matrix of a linear transformation is a pretty simple two-step process. First of all, find what the transformation does. to the standard basis of Rn, whatever dimension you're in. And then the results of what you found in step 1 are the columns of the transformation matrix. And that's it. So I want to talk for a minute about some questions that'll come up on the quiz, just kind of introduce the ideas. So one of the questions that you're going to be asked is this transformation, where you have x, y as an input, and the transformation is just this, is this a linear transformation? And it'll be a true-false question, so you really have to think through, does it follow the rules of a linear transformation? And you might want to think through some specific examples. So that's a question that you'll come across. Is that a linear transformation? So another question you'll see on the quiz is another true-false. You have a transformation that's taking you from one vector space to another, u to v. These aren't vectors, these are vector spaces. So this is a transformation. True or false, distinct vectors in U always have distinct images in V. And here we're using the word distinct to mean different. So different vectors in U, are they always sent to different vectors in V? Or in other words, could it be possible that two vectors in U go through the transformation and end up at the same image? And I guess for this one, the hint I'll give is think about being in R2 and say that your transformation is represented by the matrix 1, 0, 0, 0. This is a linear transformation. Could that ever send two different vectors into the same vector? So another true-false question, if the dimension of V, talking about another linear transformation, or a transformation from U to V, if the dimension of V is greater than that of U, so you can think of going like from R2 to R3, the dimension of V is greater than that of U, then there are no linear transformations from U to V. And my hint on this one will be, can you think of a matrix that takes you from R2 to R3 as a transformation? And what do we know about matrices in relation to linear transformations? Okay, another question you'll see on the quiz, consider the general scaling vector. That's not a vector, that's a matrix. In R3, defined by the following. Okay, one more question you'll see on the quiz is consider the general scaling of a vector in R3 defined by the following matrix S. And here's the matrix S. So this is a transformation, and we never let C equal 0 or D equals 0. Does this transformation have an inverse? So this is definitely a linear transformation, but does it have an inverse? And if so, find it. So you want to think about what this matrix does, and could you undo it with another matrix? And if so, find that matrix. Okay, this section was pretty heavy into theory, but some of the big ideas that we saw were the idea of a linear transformation versus a transformation that's not linear. A linear transformation will always follow those two rules that we talked about right here. This is what qualifies something as a linear transformation. And then we had the ideas of that every linear transformation can be represented by a matrix, and every matrix is actually a linear transformation. And then we did talk about how to find the matrix of a transformation, that two-step process.